Today we are talking about functions of several variables. So let's lay out what we're talking about here, our definitions. So up till now, in the previous chapter, we have dealt with a function r, which would take in a real number and spit out a vector, r to the m, where m was usually 2 or 3. So the input was a t, and the output was x, y, or x, y, z. Well, now we're doing the opposite. We'll have a function f, and this is a scalar. It means we are going to take in, and we'll do r2 for now, some x, y, and spit out some value z, or f of x, y. So this is the opposite of what we did in the last chapter, and so it has its own uses. So let's define what we're talking about then. A real valued function of two variables. So I was thinking of functions as a machine where you plug in one number, a machine turns the crank and spits out something else. Well, here we are taking in, instead of plugging in a single number, taking in ordered pairs. When the output is going to be a real number, so any input has exactly one corresponding output. That's the same, meaning any ordered pair can only have one output. So if we write as z equals f of x, y, then x, y are the independent variables, z is the dependent variable. And so that is this is like I said, it's the opposite of what we did before. Sometimes we will have 3 independent variables, but we'll save that for the end of the lecture. We'll focus on 2 for now. So the first things we have when we are talking about a function, we define domain and range. So R2, which is a set of 2 input vectors, 2 component vectors, is all the possible numbers we could plug in, but maybe some of them get ruled out. So we restrict to a domain D, which is some subset of R squared. And then the range is all the outputs that F can achieve on D. And we usually want to think of D as a connected subset. So let's get a visual on what that would look like. So, in 2 dimensions, we would have some blob in space, and we'll call this D. We're saying for every point you pick in D, would map somewhere on the real line. So this is an xy here, or right as a vector, and it gives z. And some other xy might go to a different z, some other xy will go to a different z. I say connected, and what connected means is any 2 points you pick, you can draw some path between them without having to leave the set. That's not a requirement, but it's pretty common in the examples we're going to do. A 3-dimensional example, appropriate to Albuquerque, would be a weather balloon. If we have a balloon up in the air, and we say we're inputting latitude, longitude, and altitude. Those would be 3 inputs, and the output would be temperature. So we're saying go to this point in space, x, y, z, and record the temperature. That is a function of 3 variables. The inputs are 3 components, and the output is the temperature. All right, so we've talked about this again, but I'll say it one more time. Previously, t was the independent variable, x, y, z were dependent variables. So in the past, you might think, hey, we already dealt with multivariables when we had a line, maybe we had x, y, and z, we were all plugging in, and so the line was based on 3 variables. But it wasn't really, because each of them were all based on the same t. So if we had some linear function, if we had, like L would be x is 1 plus t, y is t squared minus 1, z is sine of t, whatever, something like that, doesn't matter. If we knew any one of these, maybe not y, but if we knew x, we could solve for t, and then we could plug into the other. So really, t was the only variable, and all theirs depended on it. So in that case, even if it looked like there were multiple variables, there was really only one, because all the others were based on it. So let's start off by sketching domain. So let's find and sketch the domain of f of xy equals square root of x plus y plus 1 over y minus 1. And also let's find what f of 3, 2 is. So domain, we need to remember the rules we had for domain from back in calculus. There were a few the main ones we have is that does not exist when denominator is 0, when the thing under a square root, let's give it a letter. It's a square root of u when u is less than 0. Also any type of logarithm, log of u, when u is less than 0, or less than or equal. For log, you can't have 0. For square root, you can. So what we usually do for domain is we rule out everything we can, and then whatever's left over is the domain. Now, since this has 2 variables, our domain will be living inside r squared. It'll be something on the plane, but the exact values, we have to rule out some stuff. So let's look at the denominator. Well, x minus 1 cannot be 0. So therefore, x cannot be negative 1. So if we have our xy plane over here, then x equals negative 1, that's ruled out. And now let's look at our numerator. Well, it's a square root, so the thing under the square root must be greater than or equal to 0. So what do we do with this? Well, I think what we want to do is we want to solve this for y. So let's say we will subtract the x up to 1. Y is greater than or equal to negative x minus 1. Now we're going to sketch this region here. We're going to say the line, this defines a line on the boundary. Line is y equals negative x minus 1. So we will say, well, from here, we get a line with a slope of negative 1, looks like this. I'm using a solid line this time because y is allowed to equal this line. You're allowed to equal the line, whereas you weren't allowed to equal that dotted red line. And then the only question is, which side do we shade? We're saying y is greater than or equal to. Well, y means up or down, so from our line we can go up. And that's our domain, is everything that's shaded blue but is not on that dotted red line. Maybe I should erase this one so it doesn't look like it overlaps. Now, if you're not sure if you got the right side, you can pick a test point. So what is a point that is in this domain? Well, 0, 0 is in the domain. If I plug in f of 0, 0, I would get square root of 1 over negative 1, which is negative 1. That's a well-defined value. That's a number. It satisfies this equation, y is greater than or equal to, not equation, inequality, negative x minus 1, because 0 is greater than or equal to negative 1. If I plug in 0 for y and x, this is true. What we're saying here when we say y is greater than or equal to negative x minus 1 is the domain is everything where that's true, where if we plug in y and we plug in x, the left side is greater than or equal to the right side, and also x is not negative 1. So that's how you do domain. We are looking just at what is allowed to be plugged into this. And that is not the function. The function would have 3 dimensions to it because the output is a 3rd dimension. So this is just showing you what are all the points you can plug in. It doesn't tell you about what their values are. So the 2D graph here is not the same as in Calc 1 where the graph shows the whole function. At least that graph would be 3-dimensional. It's also said find f of 3, 2. So let's plug in 3 for x and 2 for y. So that would be square root of 3 plus 2 plus 1 over 3 minus 1 is square root of 6 over 2. That's it. All right, let's try another example of finding domain. So x log of y squared minus x. And again, we'll also find 3 and 2. So it's pretty similar to the last one. Let's see. Okay. First off, f of 3, 2 is x natural log, and again, if I say log, I mean natural log of 4 minus 3 would be 3 times ln 1, which is 0. Okay, now for the domain, well, we have x log of y squared minus x. The x out front is not going to have any problems for domain. It's just x. We can always plug something in there. But the ln, well, the argument here has to be positive. Y squared minus x greater than 0. So let's solve this. We get y squared is greater than x, or equivalently, x is less than y squared. Both cases, the arrow is pointed at the x. So let's define what that shape is. Oh, it's so sideways like that. All right. Now we're going to use the equal. Will just be a dotted line this time. So x equals y squared is a parabola that opens to the right. So that's our boundary. Now we say x is less than y squared. So we could do a test point. We could say, well, what about the point 1, 0? We can't use 0, 0 this time because it's right on the boundary, so it doesn't help us. So we'll plug in 1 for x and 0 for y. 1 is less than 0 squared. 1 is less than 0. That is a false statement. So 1, 0 is not in the domain. Therefore, the domain must be everything else. If I plugged in, for instance, negative 1, 0 instead, I would get negative 1 is less than 0. That is a true statement. And so I think of this like the Microsoft Fill tool. You pick the point here, negative 1, 0, and then it fills everything up to the line. It can't cross the line, but it can fill everything else that it touches. So that's our domain. And if you weren't thinking of test points, you could also look at it this way. X is less than y squared. You can say, well, x being less means the left, because x is left and right. So x must be to the left of it. All right, let's do another. Find domain and range of f of x, y is 16 minus 4x squared minus y squared all over under the square root. Okay. So that means the argument here is our square root must be greater than or equal to 0. Let's figure out what this is. Well, that is 16 is greater than or equal to 4x squared minus y squared, plus y squared, sorry. And then this is a conic section. We can divide out the 16. And like I said, conic sections, you should probably do a quick review if you don't remember how they work. Ellipse and parabola, hyperbola. Don't need to be an expert, but they are going to come up a lot in the next couple chapters. So if you need to review them, that was in pre-calculus, you probably should. Okay, so 1, next thing we'll do x squared over 4 plus y squared over 16. So 1 is greater than or equal to, if I said less than, I'm sorry, didn't mean to. X squared plus 2 squared plus y squared over 4 squared. I'm speaking words wrong, I think, but the picture's right. Okay, so that is defining an ellipse. The x goes up to 2, the y goes up to 4. So we will say here is 2, 0. Here is negative 2, 0. Here is 0, 4. Here is negative 0, 4. Went a little off my axes, but I say negative 0, 0, negative 4. Okay. And then, I don't know if this would allow me to make an, no, it might. Can I make this a little wider? Oh, how about that? There we go, that's our ellipse. Now the only question is, are we shading inside or outside it? Well, we'll get a test point. We will pick, the obvious point is 0, 0. Let's plug it into this inequality, or this one, any of them. 1 is greater than or equal to 0 plus 0. That is a true statement. So the point 0, 0 is in the domain, so therefore everything else inside that ellipse is in the domain. If it were a false statement, if it had been like a 1 is greater than or equal to 5, then we would not shade there, we would shade outside. Now range is the other thing that we need to think about. So, excuse me, let me clear most of this because I don't think we need it now. We need to think about range. All right, so f of x, y is square root of 16 minus 4x squared minus y squared. What values can this take? Well, this gets us back into our question about the rulings and the traces. We say here we got 16 minus 4x squared minus y squared. What is the smallest this could get? Well, the smallest it could possibly get is f equals 0. Because if we plugged in anything on this curve, for instance, 2, 0, that would make this be 16 minus 16, which is 0. But there's no way we can get less than that. Square root can never return negative values. And if we tried, we would end up getting imaginary answers. So the left endpoint must be 0, and it's included because we can plug in numbers to get 0. What is the largest this could be? Well, if we remember what we did here, this is f equals 0 on the boundary. As we go inward, it gets higher. The highest we can get is here at the peak. If we plug in 0, 0, we would get square root of 16, or 4. So that's our range. There's no way we can make this be greater than 4 because we're always going to be subtracting 4x squared and y squared, so it can never get more than 16, which then square rooted becomes 4. Now, if we were to plot these together, x, y, and z, and plot this egg shape here, which was the three-dimensional graph of it, z would only be in the positive this time. We would not, because of that square root. If there were no square root there, we would graph the whole top and bottom part of this ellipsoid. But since there is a square root, we can only get positive values for z. So this half ellipsoid is the graph of f. So what is a graph? You've used the term all the time, but I want to specify exactly what it means. So if we have a function from r squared into r, the graph of f is instead of all points x, y, z, where f of x, y gives you z for any x, y in the domain. So the graph is a visual representation of both the inputs and the outputs. When the domain was one variable and the range was also one variable, the graph was a curve in R2 because we had an input and an output. But now the input is 2D, the output is 3D. So the graph is surface in R3. This should definitely say 3 there. I'm going to correct that in my notes right now because that's the graph is a two-dimensional surface, but it's a two-dimensional surface that lives in the third dimension. You can't really see it if there's only two dimension. It would be too big. So that should say a two-dimensional surface in R3. If we were in a weird case where the domain was R3, that'd be really hard because the graph would be 4 dimensions. We could maybe color in spaces in 3 dimensions to give an idea, because that would be a fourth representation of the fourth variable, like say bright red for the hottest parts in 3D space and cool blue for lower temperatures. So let's draw a graph. Sketch the graph of f of x, y equals 6 minus 3x minus 2y. Well, this is dealing with planes again. So we need to get some points that are on this graph, which are x, y, z pairs. So we will plug in some points to get their corresponding z values. The easiest way to do this would be to get the intercept. So let's say if x and y are both 0, then z is 6. So 0, 0, 6. So this is really z equals 6 minus 3x minus 2y. If x and z are both 0, then we have 0 equals 6 minus 2y, so y is 3. And if y and z are both 0, then we have 0 is 6 minus 3x, so x is 2. And so then we generally represent this by drawing the tetrahedron here, that plane, and then kind of shade it in a little. Maybe let some arrows to indicate that it keeps going past there. But that's our graph. It's saying we are defining our function here that we're given. We're saying this graph represents all the information about the function. Anything that's on that plane, the graph of it, the plane is the graph, is a solution, an input and output pair. All right, there are a few more things I want to show. We talked a little about level curves in the past. And sorry, just a minute, let me get something ready for our next part. So, given f is a function of x and y, a level curve is the equation f of x, y equals k. It's the solutions of that. So, if the k's are evenly spaced, we can then get a general impression of the 3D shape. And you've seen this before in maps. You have contour maps here. So if you zoom into specific places, if they're really tightly put together, that indicates it's pretty steep there because the height is changing pretty fast. On the other hand, if they're more spaced out here or here, it's a lot less steep because that indicates that the elevation is not changing as fast. Okay, so let's draw some level curves of this one. Well, we kind of already did just earlier, but we will be a little more specific. Let's see. Though I don't think, I said before, I don't think we need to be super precise about these. I gotta be a little more precise than that. A wobbly x-axis looks weird. So if f xy is root 16 minus 4x squared minus y, well, we saw the level curve at 0 here. There's 2, 0, 0, 4, 0, negative 4, and negative 2, 0. And then, as we go inward, we get more that are, I feel like I want to say parallel. I think that would be a valid term to use, even though they're not lines. Something about their derivatives matching in the right way, but I don't know. But you get this pattern here. So those are a bunch of level curves. And like I said, we could solve for them really specifically by saying set this equal to 1 and figure out exactly what the x and y intercepts are. But I'm okay with a general shape. Let's see. Okay, what's next? Sketch a contour map for z equals y squared minus x squared with at least 3 lines. Okay, contour map is just a collection of level curves. So we just did one for one function. We're going to do it for another function. All right, so z equals y squared minus x squared with at least 3 lines. This is probably the quiz on Monday is going to be draw one of these contour maps. Okay, so z equals y squared minus x squared. So we're going to make it, let's make a table here. We're going to set a k value. Y squared minus x squared equals k. And I just use k for constant because z is a variable, but if we're saying we're setting z to be one specific number. So if k is 0, then we get y squared minus x squared is 0. So y squared is x squared. Y is not x, but it is plus or minus x. Because we take square root of both sides, we get a plus or minus. So, two diagonal lines here. And this is k equals 0. Okay, now let's plug in 1. If k is 1, y squared minus x squared is 1. So what is that? That is a hyperbola. And it's going to open upward because the y squared part is positive, so that means the y is always going to have to be greater than the x for this thing to be true. So therefore, the y equals, or k equals 1 will look like, that's a little lopsided. Close enough. K equals 1, but also this. It should not be touching, that's really bad. Keep doing that. K equals 1. See, hyperbolas are pairs. And if we did 2, so y equals plus minus x here, 1 equals y squared minus x squared, 1 is y squared, that 2 is y squared minus x squared. Well, that just makes another one of these a little farther up. K equals 2, k equals 2. What about negative values? Can we get negative values? Well, if we put negative 1, we get negative 1 is y squared minus x squared, which we rewrite as 1 is x squared minus y squared. There's also hyperbola, but in this case, the x has to be greater, so that means it's going to open to the right and the left. So there's k is negative 1, and there's k is negative 1 over there too. And then k equals negative 2 be like that. So what we're seeing is, as we go left and right, our surface will go downward, but as we go up and down, it'll go upward. Let's see what that looks like. Let's look at our graph here. Hopefully you're all seeing this. Z equals y squared minus x squared. So it looks like that. It's a saddle. And positive x, we can see as we go forward in x, it goes down, but we go forward in y, it goes up. Okay. One application that might come up, this is something in business, which is there is investment in both labor and capital, and there's a trade-off between the two values. If you have more machines, you don't need as many people, but if you have more people, you don't need as many machines. So the P here is profit, and you get these level curves. They call them indifference curves because if you're running the business, you are indifferent to how you make your profit if it doesn't change any. So tweaking the labor and capital, as long as you stay at the same profit, is no big deal. Alpha is just based on the nature of the industry. L and K are variables. So when we Plan 2, we can use x and y in place of l and k when we're graphing. So let's see what it looks like for alpha is 0.25. Now, this is not something I would, put on a test, but it's just a neat little application. So 0.25. So we'd have let me make sure. Okay, so it would be, we'll just make up some values. We'll make a value for b. Let's say 100. Is there a b here? Yeah. 100 x to the 0.25 y to the 0.75. It's really oddly shaped function. It's kind of let's look at that in. Maybe we need to zoom out a little, or. Okay, this is not as pretty as, but look at the edges there. I think there's, let's see if we can get some level curves on this. There is a setting in here to graph the level curves. Ah, here we go. Let's create a plot. Contours, show XY plane grid. Okay, this graph is not as pretty as I was hoping it would be. Let's go back to one of our other ones, see if we can get a nice picture on it. I think I just broke it. Oh dear. I zoomed way too far in, that's what happened. Or way too far out. Well, feel free to play around with this. I'm not going to mess with it anymore. Okay, let's do one more problem. Domain in 3 dimensions. So, like I said, we started with domain being 2 dimension and range being 1. But domain, it honestly can be as many dimensions you want. I mean, in some weird cases, you can have an infinite dimensional domain. But we're almost never going to go past 3. There might be 1 or 2 exceptions, but I don't think there are any in this course. And if so, they're pretty rare. So, let's find the domain of this function here. Well, it's not that different from the 2-dimensional case. We cannot have 0 denominator. We cannot have negative under square root. In this case, our denominator is a square root. So, that means, in and of itself, the square root says it can't be negative, but being a denominator means it can't be 0. So we need 9 minus x squared minus y squared minus z squared to be strictly positive. Normally we would allow 0, but since the denominator we don't. Well, it's the same as saying x squared plus y squared plus z squared is less than 0. No, it is not. It is less than 9. What is that? Well, that's a sphere centered at 0, 0, 0. Radius, I'm going to use a rho for radius. That's what we usually do for 3D, is 3. And it is not including the boundary, so it's an open ball is what we call it. We'll have a doing the whole thing in a dotted line because we do not include the boundary. We're talking about the inside or the outside here. Let's see. X squared must be x squared plus y squared plus z squared is less than 9, so that's the inside. For instance, if we plug in 0, 0, 0, we get a true statement. 0 is less than 9 is true. So we will shade the inside here carefully. Or if you don't think you can express that clearly in visual, you can just say inside of this sphere. I would accept that in words as an answer. All right. So that's it. We'll see you on Monday.